Have you ever stopped to think about how the electricity flowing silently through your walls can make a fan spin? One is just this invisible energy, and the other is real physical motion. They seem like they're from two totally different worlds. Well, today we're going to pull back the curtain and look at the incredible hidden force that connects them. All right, so this is the big question, right? This is the puzzle we're going to solve together. How does a simple flow of electrons in a wire, how does that turn into an actual physical push or pull, a force that can spin a motor or power a train? I mean, it really does feel like magic, but I promise you it's pure physics, and it's one of the most important forces that our entire modern world is built on. And check this out. This is our mystery in action. We've got a plain old aluminum rod just sitting inside a magnet. Nothing's happening. But the moment you pass an electric current through that rod, bam! It moves. It gets physically pushed to one side. This is no trick. It's a perfect demonstration of a force we call electromagnetism. And to really get it, we've got to rewind the clock and go back to where it all began. The funny thing is, this whole story doesn't start with some brilliant grand plan. Nope. It starts with a complete accident. An observation so weird that it made scientists rethink everything they thought they knew about two forces of nature that were supposed to be totally separate. So, meet Hans Christian Oersted. Picture this, it's 1820, he's in the middle of a lecture, and he notices something odd. Every time he turned on his electric circuit, the needle on a compass sitting nearby, it twitched. Now, a compass needle is only supposed to care about one thing, pointing north, but here it was reacting to electricity. This was it. This was the first real proof that electricity and magnetism weren't two different things at all, but were actually deeply, deeply connected. And what's so cool is just how simple his experiment was. Step 1, you put a compass near a wire. No current, the compass just does its thing, points north. Step 2, you flick a switch, and current starts flowing through that wire. And then, step 3, instantly, that compass needle just snaps to a new direction. The conclusion was undeniable. The electricity flowing in that wire had to be creating its own invisible magnetic field. Okay, so an electric current creates a magnetic field. But what does that even mean? What does this invisible field of force actually look like? Well, it turns out we have a pretty clever way of making the invisible visible. First, let's get a quick definition out of the way. When we say magnetic field, all we're really talking about is the area around a magnet or a current where you can feel its magnetic push or pull. You can think of it like the heat you can feel around a campfire. It's that invisible zone of influence. And this is just beautiful. If you take a regular bar magnet and sprinkle tiny iron filings around it, they don't just fall randomly. They snap into these incredible, elegant, curved lines. These lines are literally a map of the invisible magnetic field, showing us the exact pathways that the magnetic force follows. Now, these field lines, they play by a very strict set of rules. First, they always flow out from the North Pole and loop back around into the South Pole, always forming complete closed loops. Where the lines are really bunched up together, that's where the field is the strongest. And here's a crucial one. They can never, ever cross each other. Let's just pause on that last point for a second. Why is that? Why is it totally impossible for two of these lines to ever cross? Think about what those lines are actually showing us. The answer is actually really simple and kind of clever. Remember, a magnetic field line just shows the direction a compass needle would point if you put it right there. So if two lines crossed, it would mean that at that one single point in space, a compass would have to point in two different directions at the exact same time, which of course is impossible. So now we have a pretty good idea of what a magnetic field looks like. But remember, the field we're talking about is being created by an electric current in a wire. So that leads to the next logical question. What happens if we change the shape of the wire? Does that change the shape of the field? Spoiler alert, oh yeah. Okay, let's start with the simplest possible shape, just a long, straight wire. When we run a current through it and sprinkle those iron filings, we see a totally different pattern. It's not the loops of a bar magnet at all, it's perfect concentric circles surrounding the wire. The electricity creates this kind of magnetic whirlpool of force around it. So, which way is that magnetic whirlpool spinning? Well, there's a super easy trick for that. It's called the right-hand thumb rule. Seriously, you can try this right now. If you point the thumb of your right hand in the direction the current is flowing, the way your fingers naturally curl around, that's the exact direction of the magnetic field lines. It's a fantastic little mental shortcut. Now, things get really interesting. What if we take that straight wire and we bend it into a circle? You can see right away how all those little circular field lines start to add up and reinforce each other right in the middle. By doing this, we're basically focusing the magnetic field, making it way stronger at the center of the loop. And now for the grand finale. What if we don't just stop at one loop? What if we stack a whole bunch of them together to form a coil, what's called a solenoid? Well, each loop adds its magnetic muscle to the next, creating this really powerful, really uniform field inside. And just look at the result on the left. The magnetic field it creates is now practically identical to a regular old bar magnet. We've just created a magnet with a north and south pole using nothing but wire and electricity. This is an electromagnet, and it's an absolute game changer. Okay, let's take a breath. We've covered a lot of ground. We know electricity creates a magnetic field, and we know we can shape that field by shaping the wire. Now, finally, we can go all the way back and answer our original question. How does this invisible field create a real physical force? Let's go back to our aluminum rod from the beginning. Now we know what's really happening. The current in the rod creates its own little magnetic field. And when that field interacts with the field from the big horseshoe magnet, it creates a force. The really crucial thing to see here is that the direction of this force is totally dependent on the direction of the current. You reverse the current, you reverse the push. That means this force is predictable and controllable. And you guessed it, just like we had a rule for the field's direction, we have a rule for the force's direction. This one's called Fleming's left-hand rule. Grab your left hand. Point your forefinger in the direction of the magnetic field. Then point your middle finger in the direction of the current. Your thumb, well, it automatically points in the direction of the resulting force or motion. And with that, the mystery is solved. We now have a predictable, reliable way to turn electricity into motion. So this principle, that electricity and magnetism can work together to create force, is not just some neat little science experiment. It is, and I am not exaggerating here, one of the absolute pillars of modern technology. Let's just take a quick look at how much of our world is built on this one simple idea. Every single electric motor, from the one in your blender to the ones that power an electric car, it's all using this principle. They're just constantly flipping the current's direction in a coil to create a continuous push and pull that forces the motor to spin. And your loudspeakers, same deal. A fluctuating electric current from your music makes an electromagnet vibrate, which pushes a cone back and forth to create the actual sound waves you hear. It is literally everywhere. And this is just amazing. This force isn't just in our machines, it's inside of us. The tiny electrical signals, the ion currents that travel along your nerves, they create their own minuscule magnetic fields. Now, they're incredibly weak, but super sensitive machines like an MRI can actually detect them. And that's how doctors get those incredibly detailed images of our brains and organs without ever having to make a single cut. You know, understanding these principles even helps keep us safe at home. In our circuits, the earth wire is a critical safety feature. If a live wire ever accidentally touches the metal case of an appliance, the earth wire gives that huge surge of current a safe, easy path to flow into the ground, which trips the circuit breaker and stops that metal case from giving someone a nasty shock. So, from the simple, accidental twitch of a compass needle all the way to the complex machines that power our world and even peer inside our own bodies, the discovery of electromagnetism just shows us how one little moment of curiosity can reveal a hidden, fundamental force of nature. Which really leaves you with a final thought, doesn't it? What other incredible, invisible forces might be all around us right now, just waiting for the right experiment to bring them to light?